So we can combine F equals ma with the SUVAT equations because acceleration is part of the SUVAT equations, and we can calculate acceleration based on forces and masses, and we can go the other way as well. If we're given information that works with SUVAT equations, then we can then calculate our force. And we're talking specifically here, if you remember, about constant accelerations. We're not talking about variable accelerations when we use SUVAT equations. So a body of mass 5 kilograms is pulled along a rough horizontal table. So here's your rough horizontal table. Here's the mass of 5 kilograms. It's got a weight force, which is going to be 5G. It's got a normal reaction force, It's got a horizontal force of magnitude 20 newtons pulling this along. And we have a constant friction of 4 newtons. So we have a resistance force of 4 newtons. Given that the body is initially at rest, so here, this is where our SUVAT equations come in. S, U, V, A, and T. So we're initially at rest, so our initial velocity is 0 meters per second. We want to find the acceleration of the body, first of all. So if we want to find acceleration, we know we're accelerating in this direction because that's where the greater force, the 20 newtons, is. So let's resolve that way. So we have 20, take away 4 newtons in total of force resolved horizontally. But that force is equal to our mass, which is 5, times our acceleration, which we don't know. It wasn't given in the question. So 16 is 5a. So a is going to be 3.2 meters per second squared when you solve that. So we have our acceleration. So that one's done. Distance travelled by the body in the first 4 seconds. So for part B, we're given that the time taken is 4 seconds, and we want to find the displacement. All right. So we're going to use the SUVAT equation S equals ut plus half at squared. So our displacement is going to be ut, well, u is 0, so that's just 0. And half at squared, so half of 3.2 is 1.6. And then t squared is 4 squared. So it's going to be 1.6 times 16. Which is 25.6 meters. So the distance the body travelled in the first 4 seconds, 25.6 meters. Now we want to find the magnitude of the normal reaction between the body and the table. Now if we resolve our forces vertically, which we haven't done yet, we know we have no acceleration up or down. We're not moving up or down. So therefore, we're in equilibrium. So R, take away 5g, should equal 0, because our mass times acceleration, if the acceleration is 0, mass times acceleration is 0. Well, that means our normal reaction force equals 5g, which is 49 newtons. So the magnitude of the normal reaction, 49 newtons.